today what we're going to talk about is clustering algorithm. So recap, we've been talking about, mostly classification and regression problems. So, the problems that we've been working on were a set of problems where we have a set of feature vectors. And then as a result of that, we have a label associated with it. So then, the role of machine learning was to discover this unknown function f that maps the input feature vector x to the label y, right? So that's a kind of a, stereotypical formulation of supervised learning. When it comes to unsupervised learning, we don't have this supervision label y. So basically, we just have a bunch of feature vectors. And then your job is to discover some underlying structures or some patterns or some trends and etc. from the given collection of feature vectors. So that's what is called an unsupervised learning. And clustering in particular is one of the most important type of unsupervised learning problem in data science. So over the next couple of lectures, we're going to talk about the clustering algorithms. Now, to get into a little more in detail, clustering is about grouping of data objects such that in each group, we have the objects that are similar to one another. And then, further, if two objects are in different groups, then, it is likely that the two objects are not so much related to each other, so much similar to each other. So, finding this kind of structure is what clustering is about. Now, when we do that, here are two important concepts. So, in the last module, we talked about the concept of distances. And in particular, in clustering, we're interested in two different types of distances. One is the distance among the objects that are within the same cluster. So those are called the intra-cluster distance. And what we want to do is to minimize the intra-cluster distance. Obviously, when we set a cluster, we want to set a cluster in a way that the distances among the objects that belongs to the same cluster are minimized. So for example, let's say, we have 3 data samples, okay? Obviously, it is better to cluster them like this as opposed to, cluster them like this. Because in scenario A, as opposed to scenario B, we have the distance between the objects in the same cluster to be much smaller than the case B, right? So it is kind of, almost like a common sense, right? You want to minimize the, distance among the objects that are, within the same cluster. Similarly, we also consider the notion of inter-cluster distances. And in case of inter-cluster distance, we want to maximize them, meaning that we want the boundary between the cluster to be as clear as possible. So again, in a similar logic, you probably don't want to split this, 2 data points because they are very close to each other. So then the boundary becomes, a little fuzzy. So by maximizing the inter-cluster distance, what you're achieving is, a clear distinction between the objects in a different clusters. Okay, so it's kind of, sort of a typical, almost like a common sense, but it is always good to kind of emphasize what are being minimized and what are being maximized. Now, the clustering task, mathematically speaking, we're interested in the partition of the data space. So partition is a mathematical, term that is about, splitting a space into several regions that are disjoint to each other. And so that, the union of partitions, let's say, we have n partitions, then the union of those n partitions must be the total set. Well, let's call it omega. So if omega is our data space, we want the union to cover the entire data space. Plus, like I just said, we want them to be disjoint. So meaning the intersection between two partitions needs to be empty set if I and j are different, right? So for different partitions, there's no overlapping region. So the subsets P of the original set omega are called partition of the space when they satisfy these two conditions. Okay. So basically, a clustering task is to find the partition from the data space. Okay. And as far as it satisfies these two conditions, you can consider it as some solution to a clustering task. And of course, while satisfying these two conditions, we want to promote these two things. We want to promote smaller intra-cluster distance, and then we want to promote a bigger inter-cluster distances. Okay, so that's roughly speaking what clustering is all about. So then regarding that, there are some questions arise. First is how to define the distance, right? So this is something that we discussed last time, right? Where the distance function is a numerical metric to kind of capture the notion of how similar two objects are, right? Or dissimilar the objects are. And, building upon that, we also want to define what is a good partition. Okay, so how to measure the quality of clustering. We kind of, in an abstract way, stated that a good clustering is, the one that minimizes the intra-cluster distance and then maximizes the inter-cluster distance. But in fact, if you think about it, there are many different ways of defining the intra-cluster distance, and there are many different ways of defining inter-cluster distance. Hope that makes sense. So we're gonna go deeper into those topics pretty soon. Now, to do a more technical discussion, let us kind of agree upon some convention. So this is kind of what we've been dealing with, the data matrix. This is basically a data frame, right, where we have number of rows representative of each different observation and different instance, and then we have a number of different columns representative of the number of features, right? And that's basically how the data matrix X is structured. And then the distance matrix is what we define as an object that represent the distance between the ith object and the jth object. So the distance matrix, this is something that we discussed last time. It's an n by n matrix where n is the number of object, and then the ijth element of the distance matrix is representative of the distance from the ith data point to the jth data point. And then, because of that, obviously, the diagonal component is all 0 because it means the distance from the ith object to ith object itself, right? And then they're symmetric because the distance from I to j is the same as the distance from j to I. So that's how we define the distance matrix. Now, we're going to use these two notions to define clustering method mathematically. Now, there are two different types of clustering methods. One is a class of method that belongs to the category of hierarchical clustering. And then there's another kind of method that belongs to the partitional clustering. So in today's lecture, we're going to compare two different methods. More particularly, we're going to introduce a k-means clustering algorithm, which is probably one of the most popular clustering method out there. And then we're going to compare that with the agglomerative clustering, which is again another very popular way of conducting a cluster analysis of a data set. Okay. So in terms of the basic concept, like what we previously discussed, we want to construct a partition of a data set, okay, which is comprised of n objects into a set of k clusters. And the condition that the partitions had to satisfy was that the partitions had to be disjoint to each other. And what that means is each object should belong to exactly one cluster. No more, no less, just one cluster. Okay? Because otherwise, if an object belongs to more than one cluster, then the intersection between the partition I and partition j may not be the empty set anymore, right? Or if there's an object that doesn't belong to any of the cluster, then that means, we don't, really satisfy this condition, right? Because if we have a cluster that, if we have an object that doesn't belong to any of the cluster, then that means, there are a subset of objects that doesn't belong to any of those PIs, so that the union of the PIs is going to still exclude the object that doesn't belong to any of the partitions, right? So we will not going to be able to satisfy this condition. Okay, so no more than one and no less than one, just exactly one cluster is the condition. Now, this is kind of a tricky part, the number of clusters. Usually they're given in advance. It's usually the parameter that you have to kind of fine tune. Sometimes by the nature of the problem, the K is given already. But nonetheless, many of the clustering algorithms require you to satisfy the number of clusters. There are exceptions, in fact. For example, hierarchical clustering doesn't assume any predefined number of clusters. We're going to also talk about what is called a DB scan later. And that algorithm as well doesn't assume any particular number of clusters. But other than those particular scenarios, a lot of times the number of cluster is something that needs to be given in advance. Okay, and that's especially true with the k-means clustering. Okay, so k-means clustering is probably one of the most popular algorithm out there, and the reason for the popularity, I think, is because of the simplicity of the algorithm. And it's quite scalable, actually. So today we're just talking about the k-means clustering in general, but later on we're going to learn that k-means clustering is also kind of applicable to big data problems. Okay, so k-means clustering is a very simple algorithm, but in fact very powerful algorithm as well. So k-means clustering begins with an idea of representing a cluster using the mean of the data points. Okay, so the idea is pretty simple. I love to use this metaphor of electing a representative. Okay, like in politics in human society. So let's say we have a number of points like this, and then we choose the representatives based off of the average or the mean of the data points. So the idea is basically whoever is the best representation of a given group is an average individual that has the smallest distance to each other. So mean, in some sense, is an object that minimizes the distance to each of the members in the group. So for example, let's say you have 2 points, and then if you pick a point over here and then measure the distance like this, versus you pick a point over here and then measure the distance like this, we know that the case and the letter has a smaller sum of distance as opposed to the case and former, right? So in fact, it is quite simple to mathematically prove that the mean of the 2 points, the average of the 2 points, has the smallest distance, smallest sum of distance, to each of the data points. And same thing when you have, 3 data points, 4 data points, and, total of n data points. Okay. So basically the error function is defined as the distance from the individual member xt, okay, and then the representative element of that particular class. And then if you minimize the summation of the distance, I think the equation is yeah, I think the equation has a little bit of typo here. I think the sigma and the min symbol has to be flipped. Yeah, yeah. So sorry about that. I think the summation symbol and the min operator has to be flipped. But anyways, if you define the error function of clustering as like this, at the end of the day, this is exactly the definition of the average point of a cluster. So the problem boils down to actually to a problem of finding the average of each individual cluster. Okay. So to kind of summarize, okay, building upon this, what's really happening in the k-means clustering is, first of all, you have data set. And then, let's say the, user defines k, and let's assume in this toy example, k is given as 2. And what happens is, we randomly just throw an initial guess in terms of where the means are located. And then from the means, we're going to partition the data with respect to the mean. And then we're going to fine tune the mean by taking the actual average of the data points and then update the mean according to the actual average. And then as you repeat this process, you will eventually converge to nice clustering that splits the data set in a way that minimizes the intra-cluster distance as defined by this error function. Okay. Now, solving this is actually an NP-hard problem. So if you're not familiar with the computational complexity theory, NP-hard means it is very, very expensive, and there's no known algorithm that is guaranteed to give the optimal solution. So what it means is, when a problem is NP-hard, it means basically it is very, very, very expensive. And even if you find something, there's no guarantee that the solution that you found is the best solution guaranteed. Okay. So in fact, solving this equation, again, sorry, I think I made a mistake in the equation. But solving this for a global minimum is an NP-hard problem. Okay. Meaning that there's no known solution to solve this, but there is actually an algorithm called a Lloyd's algorithm that is pretty effective in finding local minimums of this error function defined over here. Okay, so what that means is it is not guaranteed that the Lloyd's algorithm is going to give you the global minimum, but at least it is pretty effective in finding the local minimum of the solution. So the Lloyd algorithm, I'm going to show you with a diagram, but as you can see over here in the pseudocode, is very, very simple. There's not a lot going on. Essentially, what you do is to initialize means in random, and then basically just update the means based on the actual mean of the cluster. So I'm gonna explain this a few slides later with a more intuitive diagram. So you don't have to understand the pseudocode right away. But my point here is the Lloyd's algorithm. Okay, so the problem of k-means clustering is an NP-hard problem. So there's no known algorithm that can that is guaranteed to give you the best solution all the time. But the Lloyd's algorithm is pretty effective in finding the local algorithm, which may or may not be the best solution that you can get. So, and then, depending on the way that you initialize the means, the, final solution that you'll be getting may be different. So in terms of stability, Lloyd's algorithm is not that stable because depending on the initialization, you can have a bunch of different solutions at the end. Now, without explaining too much about the theoretical aspect, here's kind of an illustration of how the Lloyd's algorithm works. And viewing this is going to be actually quite useful for you to develop a, kind of a solid mental picture of what's going on. So let's say we have a data that is distributed like this. And, with our naked eyes, we can see that there's some sort of a structure, right? There's some, set of points going on like this, and then there's some set of points going on like this. Okay, so this is obviously a 2D kind of a class example, the toy example. So it is clear to see with naked eyes, what kind of structures exist. But in real world problem, it is not going to be, two-dimensional space anymore. It's going to be a higher dimensional space where, it is impossible to visualize. And then the structure is going to be way more complicated in the real world. But just to illustrate the process, let's assume this toy example. Now, what we do is we just generate some random values. So here, as a user of this Lloyd's algorithm, I'm going to set k equals to 2. So that's the That's the user input. And from this input, what we do is to, initialize the mean values randomly. So let's call this orange dot to be mean 1, and then let's call this blue dot to be mean 2. Okay. Now, given this randomly initialized mean, what we're going to do is we're going to visit each individual point in the data set. For example, this one over here. And we're going to compare the distance from M1 and then the distance from M2. If it is closer to M1, we're going to color code this data point in orange. If this is closer to M2, then we're going to color code this point in blue. So as you can see, this particular point is closer to M2. If we pick a point over here, this is obviously closer to M1. So this one is going to be colored in orange. And then in fact, if I do this for all of the points in the data set, this is going to be the picture that I'll be getting. So as you can see, there's kind of a line going on because we're basically, dividing the data set based off of the distance to each of the mean. So, with respect to the line that kind of is in between the blue dot and the orange dot, right? This is kind of a line that perpendicularly, bisects the region between the orange dot and the blue dot. And then things that are, on this side are going to be colored in blue. And then the things on this side is going to be colored in orange. And that's the current solution, okay? So that's the clustering result at the first iteration, okay? Now, in the next iteration, what we do is then to compute the average, compute the mean of the actual data points, okay? So we visit all the blue points over here, and then we compute the mean of those blue points. And then it's going to end up somewhere over here, as you can see. Similarly, we visit all the orange points. And then for the orange point, we compute the mean of the orange points. And then that's going to end up somewhere over here. And according to that calculation, we update the means. So as you can see now, the big orange dot has shifted from here, the original randomly initialized solution, to this location over here. And then same thing with the big blue dot, which was originally here, randomly initialized, now has shifted to this location over here. Now, since the mean have moved from one point to another, now the membership has to be updated, meaning that we're going to visit all the data points, okay? And then we're going to repeat the same procedure. We're going to compare the distance from the orange dot and then the distance from the blue dot. And then depending on which one is closer, we're going to update the membership. So it is likely that the points over here, which was originally classified as blue dot, are likely to be updated as the orange member. Similarly, the dots over here, which were originally colored in orange, are going to be updated in membership to become blue dots. So in fact, after doing that calculation, this is kind of an updated cluster. Now what we do again is to update the mean. Okay, so now based on this new membership of blue points, we're going to update the actual mean of the blue points, which is going to result in a shift of the large blue dot, the mean, to this location over here. Same thing with the orange dots. The actual mean of the orange dots are going to be located somewhere over here. So the big orange dot over here is going to be shifted towards that direction. And in fact, this is what happens after moving the mean to the actual mean of the members. Now, that's the solution after the second iteration. So basically, we repeat this process over and over again. We first randomly initialize the means, and then next update the membership of the data. And then, based on the updated membership, we move the mean to the actual mean of the updated members. And then based on that, we update the membership again, because the mean has shifted from one location to the other. And then, as you repeat this process over and over again, at the end, the algorithm converges to a certain configuration. Okay, so this is an actual solution from what I simulated using some numerical values. And then as you can see, K-means clustering is fairly good at splitting, two clusters here and there. Okay. Again, K-means is far from perfect because it is not guaranteed to converge to the global solution. So, for example, in my case, I'm a little bit bothered by, the clustering result of this part. I feel like this should be, closer to orange. But, this is what the K-means clustering has came up with. And in fact, depending on where I initialize my means, there could be many different, outcomes of K-means clustering. So again, it is not that stable in terms of, how consistent the result is, but it does a fairly good job in a, relatively small number of iterations. So, that makes K-means clustering pretty effective in many of the problems. Okay. All right. So here are some facts. Again, it is an NP-hard problem, so no algorithm, not just the Lloyd's algorithm, but also other possible ways of finding the clustering according to this error function. There's no global solution guaranteed, but as far as the Lloyd's algorithm is concerned, each iteration is designed in a way that it cannot increase the error. So what I mean by that is, okay, so we move the mean, right? We move the mean by shifting the original mean to the actual average of the cluster members, right? And that operation is always guaranteed to reduce the error function as defined over here. It is always guaranteed that each step of the Lloyd's algorithm is going to somehow reduce the error value. Okay. To be more precise, it's not always reducing it, but it cannot increase. So the worst case scenario is that the error function, the error value stays the same. Okay, that's the worst case scenario. It can never happen that the error increases from the previous step. So it's kind of nice property to have, right? The more iteration you perform, you're always kind of guaranteed to improve solutions. So there's nothing to lose, in fact, right? So that's one of the facts about K-means clustering using Lloyd's algorithm. Usually K-means is pretty fast because if you think about it, it's a fairly simple computation. And the number of iterations is generally very few. You don't really need that much of iteration many of the cases. And usually the number of iterations is generally less than the number of data points. So that makes K-means algorithm quite suitable for big data problems, in fact. Having a larger number of points doesn't mean that you're going to need more iterations. So it can be pretty fast. And if you think about it, it is easy to distribute the computation. So that's actually the topic that we're going to talk about in the next class. But for now, let's just move on with the fact that K-means is pretty fast. I think I enoughly emphasized the fact that K-means algorithm is for local optimum, not global. I'm going to move on to stress out the fourth bullet, that the choice of initial point can have a large influence in the result. So like I said, depending on how you set the initial mean, the solution of K-means, the result of K-means could be largely different. So usually because of this fact, what people do is to perform K-means clustering with different initial conditions, and then they solve it multiple times, and then try to take the average or the most frequent set of clusters as the final solution. It is not a very good practice, a very desirable practice, to apply K-means clustering only once and then just make a conclusion. Okay, when you don't have too much of concern with computational burden, it is always recommendable to perform K-means clustering multiple times and then try to take the average of the multiple different outputs. There's a question in the chat who's asking, how are the number of iterations determined? That's a great question. Usually, the number of iterations is determined by the improvement of error. So after each iteration, what you're going to do is to measure delta error, okay? Meaning how much of improvement was there after each iteration. When the delta error is below certain threshold, that's the point where you're going to terminate the k-means clustering algorithm and then declare that the convergence of the solution. Another way of measuring this is to measure the change of membership. So I'm gonna just call it a delta M. So if I go back to this example, after each iteration, the points over here, for example, they change their membership to a new orange cluster. Similar thing. These were the points that were previously orange, now become blue. And then if I go one more iteration, there's another change of membership. So what you can do is you measure the number of changes in membership, how many data points move from one cluster to the other, and then you can declare the convergence of the algorithm when delta M is below certain threshold. Okay, so let's say you have 1 million data points, and then you're going to say the algorithm has converged when the delta M goes below 100. Okay, so then that means out of 1 million members, only 100 individual data points change their cluster after each iteration. And that much, 100 out of 1 million, it is quite likely that just the noisy observations. So it's not really worth it to run the algorithm any further, right? So that's usually how people determine the number of iterations, when to terminate the algorithm. So that was a great question. Now, since I just talk about all the good things about k-means clustering, now I'm gonna talk about some limitations of k-means clustering. So let's consider this another toy example where now we have 3 distinct clusters. So I've color coded in blue, green, and red, but they're in fact originally there's no kind of pre-assumed color coding. So just assume everything was gray dots. Now, an optimal clustering, so this is probably the globally optimal solution, okay, is to cluster the points in a way that preserves the actual structure of the cluster. But you have to keep in mind that the k-means clustering algorithm will give you a different result each time you use a different initialization. And in the worst case scenario, you may converge into this weird clustering result where these two seemingly distinctive data clusters are actually clustered into one single cluster, and rather this big chunk of the cluster, which seemingly is one single cluster, is now split into 2 different clusters. Okay, so that's what I said about the local minimum and the global minimum. This is definitely one of the local minimum. So numerically speaking, there's nothing wrong with it. It has converged to a point where there's no further improvement can be made. Okay, but intuitively thinking, this is not very good. You don't want to cluster your data points like this. And you may think that this is kind of a made up example, just to point out the limitation of k-means. But in reality, you actually come across this kind of situation quite a lot, even in the real world problems. So like I said, it is always important, if the computational time is allowed, it is always desirable to conduct k-means clustering multiple times using differently initialized weights, and then kind of aggregate the result to derive a final conclusion. And when you aggregate that, for example, from a standpoint of an individual data point, let's say one time you initialize the means like this, the other time you initialize the means like that, and then you initialize the means like this, and then you perform 3 or 4 trials. And then from this individual points perspective, it was once clustered with these members over here, but then in the next clustering scenario, it has been clustered with these members. And then in the next scenario, it was clustered with these members. So statistically, we're going to have some sort of a distribution in terms of, which members this individual point is clustered with, right? And then based on that statistics, you can make a conclusion in terms of where this point belongs to. So then by doing that, this kind of a suboptimal scenarios are going to be kind of, phased out, right? Because statistically and probabilistically, these are more, likely solution that the Lloyd's algorithm will converge, as opposed to this case over here. Okay, so that's kind of a thing that I really want to emphasize. So in case of MATLAB, for example, they even have an option where you can specify how many times you're going to run k-means. So keep that in mind. I've seen a lot of people just prematurely drawing a conclusion by applying k-means algorithm just one time, and there's a very, very good chance that the clustering result from k-means is not an accurate representation of what's really happening. Okay. Here's another scenario, another hypothetical scenario where k-means clustering may not be that effective. Let's say we have 4 data points, and then the user specified k is 2. Now there is a chance that the solution converges like this, right? And this is perfectly fine if you think about it. C1 is right in the middle of x1 and x3. C2 is right in the middle of x2 and x4. So the membership becomes like this, and then it converges. There's no further improvement from this scenario. Okay. And you may think that, well, this is okay. What's the problem with this, right? But now consider this case. Let's say I've initialized mean randomly over here, and then initialize the mean randomly over there. Okay, it doesn't really matter. So even if we have it like this, with a high chance, initial clustering is going to be that x1 and x3 is going to belong to this guy over here, and then x2 and x4 is going to belong to this guy over here. And then immediately after that, when we update the mean, then this guy is going to move to the middle of this x2 and x4, and then this guy is going to move right in the middle of x1 and x3. And then that's when the algorithm converges. It doesn't further improve. So k-means converges immediately. And obviously, at this point, you realize this is not a desirable result, right? Obviously, if I go back to this original setting, I think anyone with a common sense will say these two and these two are in the same cluster. I don't think not so many of the people will say this is the cluster, right? Because one of the qualities that a good clustering has to satisfy is to minimize the intra-cluster distance and to maximize the inter-cluster distance. So in that sense, splitting the points like this is not a very good idea, and it's really just against the common sense. But there's actually a very good chance that the k-means clustering will converge like this immediately, and then never improves anymore from this local minimum. So those are kind of a two really stereotypical, well-known limitation of k-means clustering. Another thing that I really didn't prepare the slide is the selection of k. And this is something actually we're going to discuss later. But the examples so far that we discussed, we somehow assume that there was a nicely defined k. But like I said, in the real world, the data distribution is not visible. There's no graph that can perfectly visualize the data distribution in lots of real world problems, right? If you have a 2-dimensional data, you don't even need a clustering algorithm. You just plot a graph, and then you can manually cluster everything, right? So usually you have a high dimensional data, which is really impossible to visualize, and you don't even know how many clusters are there visually. So like for example, the scenario over here, the toy example over here, if we imagine that the distribution was not in 2D, but some high dimension, let's say 10 dimension or 20 dimension or 100 dimension, then we don't even know that there are 2 clusters. So then what you will need to do is to then somehow find a way to determine k, right? And that's actually a very, very tricky problem. So there are some systematic search methods. There's, for example, one popular thing is what is called an elbow method. So if you have already taken a machine learning related class, you probably heard about this Elbows method or statistical learning. It is basically a method where you plot the error versus the number of clusters K, okay? Ideally, you would want something like this, and then here's a sweet spot, and that's your optimal K, right? So if the situation is really like this, then what you can do is, you begin with K equals to, say, 3, and then maybe 5, and then 10, 20, 50, 100. You somehow kind of, divide this number of K into, some experiment points, and then you conduct an experiment, and then you find a curve like this, and then pick a point that, where the error is minimal. If that was the case, I think, no one is going to, really worry about how to determine K. Unfortunately, the real situation is that the error continuously decreases. Okay. Why? Let's consider an extreme example where K equals to N, which means we have the number of clusters K that is the same as the number of data points. So one data point, one individual data point becomes a cluster. Now, in this case, what is the intra-cluster distance? It is 0, right? If one data point is one cluster, then the mean of this cluster is going to be that point itself. And then the distance from the mean to the data point is going to be effectively 0. So when K equals to N, the error in principle can converge to 0. Does that make sense? Versus when K equals to 1, which means there's no actual clustering, just entire chunk of data is going to be considered as, one whole thing. Obviously, that's when the intra-class distance gets maximized. There's no way to find a point where the distance from this point to all the others gets close to 0. So that's going to be when the error is going to be maximum. Does that make sense? So if you consider these two extreme examples, you can easily imagine that the error curve with respect to the number of clusters K is going to always decrease like this. Okay? Which is kind of a trivial solution, right? The more K you have, the lesser error you're going to have. Now, in terms of determining the optimal K, that's a very unfortunate scenario. Because if the error curve was like this, then you could just select the one that is at the bottom. But now we have this situation where the error curve monotonically just decreases. So because of this case, there are some systematic ways to define the optimal K. So Elbows method is one of the methods that uses this error curve to determine the optimal number of K. There are many other methods to define when K is the optimal. But for now, in order to avoid getting too technical, let me just stop here and then move to the next discussion. So the main takeaway message from what we just discussed here is K-means is very sensitive to the initialization, and then there's a good chance that the solution converges to a suboptimal solution. And then finally, determining K is not always straightforward. So those are the three main kind of disadvantages of K-means clustering. Which brings us to another kind of family of clustering method, which is called the hierarchical clustering. So the idea of hierarchical clustering is kind of an opposite from the K-means clustering in a sense that this is kind of a bottom-up. So what happens here is, instead of just explaining too much about the theoretical aspect, what's happening over here is we basically compute the distances across the pairs. Okay, so we compute the distance across all possible pairs, and then pick the one that has the smallest distance. So let's say in this setup, these 2 points has the smallest distance, and therefore they become the first cluster. Now we repeat the same thing. We compute the distance across all pairs. And then in case we have already a cluster, we consider this cluster as a whole and then compute the distance from an individual point to a cluster. Okay. How to compute the distance from a point to a cluster? We're going to talk about that later. Let's for now just assume that there's some way to measure the distance. And then what we do is then, among all possible pairs that you can think of, find the one that has the smallest distance. And that's going to be the next cluster. We repeat the same thing again. Okay. So find all possible pairs. And then in case where we have already clusters, we're going to consider a cluster as a point, and then we're going to compare the distance. And then from that, we merge 2 points together, we merge 2 points together, we merge 2 points together, and then we're kind of, bottom up, we're building a hierarchical structure. So as you repeat this kind of process over and over again, this cluster is going to be merged with this point, and they're going to form a new cluster that looks like this. And then, as we do this one more time, these 3 points are going to be clustered together. And then, as we keep repeating the same thing over and over again, then we're going to see that the clusters kind of getting merged to each other and then finally become one. Okay, so that's basically what is being represented in this diagram over here, which is called a dendrogram. Okay, so with that intuitive explanation, let's kind of compare this dendrogram with the figure on the right. So as you can see, we initially have data points represented as black dots. So we originally have only 6 data points. So here's point 1, point 2, point 3, point 4, point 5, point 6, right? And then what we do is we compare the distance of all pairs. So basically we need to construct a distance matrix. Okay, distance from 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, and then 2 to 3, 2 to 4, 2 to 5, 2 to 6, 3 to 4, 3 to 5, 3 to 6, 4 to 5, 4 to 6, and 5 to 6, right? So then, that's going to construct a, lower triangle of the distance matrix or the upper triangle of the distance matrix, and then pick the one that has the closest distance. And let's say in this toy example, point 1 and point 3 had the closest distance. Now, with that, what we're going to construct is a connection in this graph where the height, okay, is the actual distance between point number 1 and point number 3. Okay. Now, after that, we do the distance computation again. Okay. So again, we compare the distance, between all pairs. And then when there's a cluster already, we're going to consider this whole cluster as a one single point. So we compare the distance from the cluster 1, not the individual data point 1, but cluster 1 to point 2, cluster 1 to point 5, cluster 1 to point 4, cluster 1 to point 6, and then point 2 to point 4, point 2 to point 5, point 2 to point 6, and just find all possible pairs. And then let's say a pair formed by point 2 and point 5 is the closest, and that's going to become a next cluster, and that's represented in this graph over here. Again, the height is the actual distance between point number 2 and point number 5. Again, in this setting, we repeat the same thing. And then next time, this time, the pair formed by, this cluster over here and point number 4 turn out to be the closest pair. So then they are kind of getting merged to form a new cluster. And that's represented by this graph over here, this part of the graph over here. Okay, so again, the height represents the distance from the cluster to 5 and then the point 4. So as you repeat this process, eventually you will converge to this kind of graph showing the pairing of the points, right? And then how the clusters are formed in a kind of a hierarchical manner, starting with the bottommost cluster to a gradually a bigger chunks, and then the heights are basically indicative of the actual distance. So this graph particularly is called the dendrogram, and simply speaking, the process of constructing a dendrogram is called a hierarchical clustering. Now, before to talk about any further details, here are some advantages of hierarchical clustering. First of all, this is kind of a big thing. We don't assume anything about the number of clusters. We're just keep merging the points together until we have no other pairs to merge. So that's kind of nice, right? Because you don't have to make an assumption on the number of cluster k. And then, like I said a few slides ago, usually the error versus number of cluster curve is like this. So it's really hard to determine where the optimal k is, right? Versus hierarchical clustering, does not need the predefined k, which makes it much easier to analyze the structure. Then how do you define the optimal number of clusters? Well, by looking at the dendrogram. Okay, so what I mean by that is basically, you can decide to, for example, cut the dendrogram using a certain distance threshold. So I'm going to guarantee that, between the cluster, there's at least 0.2, units of distance between the cluster. So then anything that is below this line is going to form a cluster, which in this case, we're going to have a cluster formed by these 5 points, and then a cluster that is formed by a single 0.6. You can lower the threshold, obviously. So instead of saying, well, I'm going to be okay with, as far as my clusters are splitted, at least 0.1. So then that's going to be the line where you cut this dendrogram, and things below that threshold is going to automatically form a cluster, which in this case, we have 4 clusters. One cluster formed by 0.1 and 0.3, another cluster that is comprised of 0.2 and 0.5, and then there's a single point clusters, one for 0.4 and one for 0.6, right? So, having this dendrogram is actually very, very nice in terms of understanding, what kind of cluster structures exist. So compared to k-means, which is, which relies on some, guesswork in terms of how many clusters are there, hierarchical clustering gives you a better idea and, more scientific evidence in terms of, what kind of structure exists in your data set. Also, it may, reveal some meaningful taxonomy. So, since this is a hierarchical clustering, you may also discover some meaningful and useful kind of categories and, subcategories and, things like that. So that's kind of another advantage of hierarchical clustering. Okay. Now, there are a couple of things that we didn't really delve into. One is we somehow assume that there's a way to measure the distance from a cluster to a cluster. But how do you do that, right? In order to be able to construct this dendrogram, at some point you will need to compare the distance from a cluster to a point, or from a cluster to a cluster, right? And how do you determine the distance? If you think about it, let's say we have a cluster that is comprised of 3 points, and then we have a cluster that is comprised of, let's say, 4 points. What is the distance between the 2 clusters? Should we pick the mean value of each cluster and then compare their Euclidean distance? Or should we pick the closest pair between the 2 clusters and then define that as the distance? Or should we pick the furthest distance and then define it as the distance between the clusters? So it's not it's not that straightforward to determine the distance between the clusters. Another thing is, okay, if you were following my lecture throughout the semester carefully, it might have already kind of automatically alerted you the fact that we're keep computing the distances, and not just the a distance. It's like the distances for all possible pairs. And if you have taken the previous lecture carefully, it probably already have alerted you, right? Because comparing all pair distance, even with Nystrom approximation and other kind of techniques, is very, very expensive. And it sounds like we're repeating this over and over again. And gosh, right? Computationally, it's going to be really, really heavy. So in the next class, we're going to talk about those kind of issues. First of all, how are we going to define the distance between the clusters? And second, how can we effectively solve this hierarchical clustering problem without compromising too much of computational speed? And then later, we're going to talk about the limitations and some design considerations of clustering algorithm when we have a large N or large D, or rapidly increasing N. And then from there, we're going to develop some new ideas and define some better algorithm in the context of big data. So that's going to be what we're going to be doing in the next week. So thank you very much, guys, and have a great weekend, and I'll see you guys on next Tuesday.